In this module, we will give an introduction to free body diagrams using a method with an acronym I2PDL. That doesn't sound very easy to remember, and if anyone has any suggestions of how to improve it, I'm all ears. The free body diagram is perhaps the most essential and fundamental concept of this course and other courses in mechanics. Before we can do any kinds of calculations, equations, or analysis of a mechanical system, a clear free body diagram of some body, object, or system must be drawn to show exactly which forces and torques are involved. A free body diagram is a model showing forces on a body when isolated away from its environment. Every other object touching or connected to the body is somehow removed. Then the forces and torques that are external to and directly acting on that body are drawn. The free body diagram is then used to help write, for example, equilibrium equations and solve for forces that are acting on the body. And I'll point out that all these words that we see here, model, isolated, external, and direct, those are all words we'll keep coming back to, so I'll just call your attention to that before we proceed. What I'm going to present now is what I'll refer to as the fundamental principle of mechanics, part 1. And this principle says you can draw a free body diagram of anything. And I know we haven't really studied it yet, but let me just prepare you that this really can be done. You can almost look at anything you see in your house when you go out and imagine drawing a free body of something. So especially if you're curious about mechanics, and I hope you are, you'll start asking yourself how you could draw a free body diagram of just about anything that you encounter. So go crazy. So to help us understand the process of drawing free body diagrams, we're going to introduce the I2PDL method. And as I mentioned before, maybe there's a better way we can come up with to remember and name this method, but here's what I'm going to say for now, because these are the steps that I think are very essential. So the first step is isolate. We're going to isolate the body of interest, or sometimes we refer to this as an object or a subsystem, but we're going to isolate that thing that we are interested in studying. And as we'll see, that itself is a good question. We have to decide eventually in our mechanical analysis which object or body is it that we want to study. And we'll discuss later why that's important and practice how to decide that. But initially, the key here is to understand what it means to isolate a body. The second step is identify. We're going to identify the contact points where something external is touching the body or acting on it, and then identify the corresponding external bodies or influences that act at those points. The third step is postulate. We're going to postulate the actions that these external influences cause, and there's two types. One could be through a force, which we understand as pushing or pulling on something, or possibly sliding or shearing on something. We'll discuss what that means a bit later. And then there's also torques, which cause a sense of rotation, and they'll be either in the counterclockwise or clockwise direction. The next step is draw. We're going to draw a representation of these actions at the contact points using straight arrows for forces and curled arrows for torques. And finally, label. We're going to label each force or torque with a useful name or symbolic expression. So, for example, imagine you have a system like this where you have a cylinder hanging from a rope or a cable, and that cable is attached to a ring, and that ring is supported by two other cables that are ultimately supported by two walls. So at some point, all of those different parts of the system might be important for us, but for now we'll just say, let's examine this system and understand all of those several parts that it has. Notice that I have not yet posed the question. For example, I have not said, okay, determine the force in cable BC. And the point I'll reiterate is, before we would do a question like that, before we could ask ourselves, hey, tell me what is the force in BC, or do a calculation for that, we must draw a clear free body diagram of something that will help us to write a procedure and do those calculations. So this module will focus on the procedure of the free body diagram. So the first step is isolate the body, and that question then leads to which body should we choose for the free body diagram. As we discussed before, there's many parts, so we could say, do we want to draw a free body diagram of the ring, or the cylinder, or the hook, or both hooks, or one or more than one of the cables? And in reality, it depends on what we're trying to analyze. And as we'll again keep discussing, the decision of which body to select is a creative process that is often the most difficult part of the problem when students say, I don't know how to start. So we'll get better at this through practicing many examples. But for now, let's do a concrete example to get started. And let's suppose we want to say, let's isolate the cylinder D. And what that basically means is we're going to cut out or crop the cylinder free from its surroundings. And then the cylinder is then what we'll call our isolated body. Okay, so in that animation, we just isolated the cylinder away from the rest of the system. And we no longer care about any other parts of our system. Okay, the next step is identify. Identify the contact points and influences. So I want you to ask yourself, where and what is something external touching or acting on the body as isolated? So I think it's clear that we imagined cutting away the cylinder from the rest of the system. In particular, there was a cable holding up that cylinder. So the first thing we'll recognize is that the cable BD is acting on the top of the cylinder. Let's give that a name and a symbol. We'll call it point Q. And that blue tilde is basically a symbol to express the fact that we cut that rope at that point. And so we're identifying with both the name Q and that symbol, we somehow cut away the cylinder away from the cable BD. It's also clear from the context, we were told this is a heavy cylinder, that something else is acting on the body, presumably. That would be the weight or the force of gravity. And we'll illustrate that action point as the blue dot. And so we'll say that gravity is acting through that point, which we'll refer to as the center of mass. There's nothing else for this body. Yes, we remember there were other things like hooks, cables, walls, and so on, but given that we are isolating the cylinder D, these are all of the contact points and descriptions of the bodies that are doing the contact on the cylinder D. Nothing else in our system is directly acting on the cylinder D. The next step is to postulate then the forces or torques. And this again takes some practice. And I'll say at the outset, there are not any torques in this problem. We'll discuss that a bit more later. But let's start by intuitively thinking about what we can probably figure out just from, having played with things. Like we've all played with ropes. We know that ropes can pull on things, right? We've all felt things that are heavy and they tend to fall down when they're not supported. So let's say, for example, how do these external influences act on the body? And we already discussed that point Q was acting the cable that is really known to be touching the top of that cylinder. So we could say that the cable BD is pulling upward. And I think it's clear that the cable can pull and it cannot push. So in this case, since the cable is vertically aligned, it can either go up or down, but in this case, pulling means it will pull up. So we're going to draw an arrow pointing upward. Okay, and think about that this does somehow look like pulling. That red arrow is pointing away from the edge where we cut the cylinder, so it's not pushing into the cylinder, it's pulling away from the cylinder. That's what that arrow is trying to say. Now with gravity, we also know that gravity pulls us downward toward the Earth, and so we'll symbolize the gravity force with an arrow going down. And I'll repeat, there's nothing else to draw on this picture. Even though there were, for example, two other cables, and those cables definitely transmit forces, those cables do not directly act on the cylinder, so therefore those cable forces are not shown on this picture. And later we'll learn some general rules that will help us to decide in general directions of how forces and torques act on bodies. Let me just give you a little philosophical comment before proceeding. The cable BD that was originally acting on the cylinder has been replaced by the equivalent force that it exerts. In other words, if you were the cylinder, imagine you are the cylinder, and you close your eyes, and someone secretly removed the cable, but at the same instant they put back the equivalent force on you that the cable was doing, then you would not know the difference. So the force is meant to be an exact equivalent action as what the cable itself was doing. Now, on the other hand, the force of gravity inherently acts as a force from a distance. It's not done through the physical contact of material. It's not tied, it's not screwed in, it's not welded. So intrinsically, gravity is always expressed as an arrow coming from the outside anyway. Okay, the next step of our procedure is label. We're going to label every force or torque that we drew. And before we do the labeling, let me point out that force and torque arrows are essentially vectors, and they should then be given names that represent what they're doing. So you've already had some experience with our last modules on vectors. This is going to be a bit of a repeat and review of that. So for example, let's look on the left and say we use a scalar labeling system. What I'll do, for example, is I'm going to label the force in the cable TBD. The T might stand for tension. The BD might represent it's going between bodies B and D, so it kind of means something. But again, I'll use a scalar symbol to say that that T is the magnitude of the force represented by that arrow. It's the magnitude. In similar way, we use mg, the mass times the gravitational constant, to represent the magnitude of the force of gravity pulling down on the cylinder. You also learned about mixed labels. And with mixed labels, as you know, it's going to be a combination of a scalar and a unit vector. So for example, I could equally refer to the cable force as the magnitude TBD multiplied by the J unit vector. And of course, the J unit vector is understood to be a unit vector pointing upward. And for the gravitational force, now since it's pointing downward, I'm going to put minus mg times j, because mg is still the magnitude, but now it's pointing in the negative j direction. And just to be concrete about this, we'll bounce in here the I and j unit vectors to make sure that that's clear. And the third way of doing this would be with pure vector labels. And so in this case, I'll use a vector symbol for t, and still I might use the subscript BD. So now we have a vector symbol for TBD, and we have a vector symbol where I'll now use G vector as the symbol for the gravitational constant multiplied by its vector direction. Okay, so I have m times G vector representing abstractly the force vector caused by the force of gravity. So just stare at all these different versions because you will see all of these in our course. I tend to emphasize the use of the scalar labeling system. In that system, again, all of the labels are magnitudes. So that's why in this case you don't see any negative signs. But when you pass to the middle example, you'll see that I do put a negative sign because I'm using the direction negative j to describe the direction of the arrow. Whereas in, again, the first case of the scalar labeling system, the arrow is already pointing downward, and that implies the direction. I'd like to bring up one more point as we're discussing this. You might have seen in the textbook the phrase particle. And the particle is meant to be a model of a system where the dimensions are not important and all of the forces are concurrent, which means they pass through the same point. So here, our cylinder would represent a system of concurrent forces because the T and the mg both can pass through the same point. They're on the same line of action. Okay, and so you might see in several books, especially in physics, that you can then just draw a dot to represent that entire body and still draw the two forces, but this would appear to be a simplified version of that system. And you could even then say, could I reverse where I draw the forces? And mathematically, this is also correct because the T force is still acting upward, the mg force is still acting downward, and they're still in the same line of action. So again, mathematically, these are correct. However, in engineering, the actual object should be drawn to approximate scale, placing the forces at the locations where they are applied and where their physical sense is, which means not only their direction, but what are they doing? Are they pushing or pulling? So for example, in the last diagram, I would interpret that as since the T is on the bottom, it looks like the T is pushing up from the bottom. And it doesn't really make sense because the T, being a force of a cable, would not push on something, it would pull on something. So I think that the idea of representing the cable force as pulling would be an important thing. Okay, but in general, we want to get in the habit of drawing the body itself with some approximate scale and detail. So I'm going to ask you to avoid using these last two models for free body diagrams in this class. Even though you might have seen them somewhere else, even though they're mathematically correct, they don't give you the full training for future engineering problems that we will need to do. So one final thought before we end this module is about known versus unknown forces. This is also a very important thing to consider when we draw a free body diagram. For now, I'll just explain what we think is happening here. The force TBD, which represents the force in the cable, will be here considered an unknown reaction, which will eventually be a variable to be solved through an equation. Whereas the weight, mg, is a given force, and the m can be considered to be a parameter. And it'll take a bit of getting accustomed to this, especially, for example, because I didn't give you the actual numerical value, for example, m being 5 kilograms or 10 kilograms or anything like that. But even though you say, hey, I don't really know the mass, the m again is considered a parameter which could be input into the system as a piece of input data. And you might say, but isn't TBD then the same as mg? And I would say, yes, we'll discover that, but if you saw that, maybe without realizing it, you're technically solving an equation, okay? So to be very strict about our designation, for the moment here, we'll consider the T to be an unknown force and the mg to be a given force.